So the next step is to construct the Magnel diagram to find a suitable eccentricity EX and to find a suitable prestressing force for the prestressing element. So let's go back to our first fundamental equations here. I assume that we all got to this stage. We're just trying to convert our eccentricity from the formulas. And by looking at it, we've got four equations that need to be satisfied at this top stress, and this is bottom stress, and this is the 1A and 2A are the stress limits for the prestressing element at the initial transferring stage, and 3A and 4A are the prestressing forces at the serviceability stage. So this is the prestressing element that gets prestressing forces loaded into the element, and this is the prestressing forces loaded onto the element, and the element has been in servicing, such as the life load, vehicle loads, and so forth and so on. So we need to find out the best suitable eccentricity E, and we need to find out what is the best suitable prestressing force that we need to load into the element. So we've all got to this stage, 1A to 4A, and basically we just need to find out the x and the y. So I just rewrite my equation a little bit. I'm pretty sure we can get to this stage as well. So just substitute your x to ex, which is e, and substitute your y, just representing 1 over pi. Pi is your prestressing force. So, and then you can find, I'm pretty sure you can easily find your MIs from your dead loads, and MS is from serviceability loads plus your dead loads, whatever you got. And you just substitute your numbers in there, and you got these long numbers here. And what you need to do is just to do a quick math to work out what these values are. So let's jump onto here. So, and then you solve your values here, and you substitute your values down here. So for example here, so your Z section modulus over your gross area is 0.224. So this would be your 244. You have to convert it, so it's a bit of tricky conversion. So units conversion. So this is 244, and for this 2A equation here, so this is negative 271, and for 3A this is 244, and for 4A this is a negative 271. So you can pretty much lock into your x-axis for these values. You got two dots for the x-axis, 244 and a negative 271, and for the because this is a linear equation, so this is pretty visualized tool to construct your lines here, because this is a linear equation. So over here, so this is this is constant, and this is the slope of your lines, right? So for example here, this is also the units conversion. You have to convert it into 0.805, and this is a 3.103. This is 0.65, and this is 2.603. So just be really careful about this units conversions, so don't get it wrong. And because we know this is the slope, we call it, I just call it, say, k equals 0.805, and then I can punch our calculators, just say arctangent 0.803. It gives you an angle value. So for each of them, you got angle values, 39 degrees, 72 degrees, 33 degrees, and 69 degrees. For some reason, but I need to talk about this with you later. And some of the values need to be reversed for some reason, but I don't know why. I'm still trying to figure that out. If you spot it out, you can let me know, make a comment below. But I found is sometimes I need to make a reverse degrees here. For example, here I got alpha as 72 degrees, so the lines are quite tilted up. It's not gonna, it's the lines are quite tilted up. Is not going to entering this zone here. So what I did was I have to do a reversed one, so it's going to be 90 minus 71 degrees. So it's going to be so it's going to be 18 degrees for my 2A line. The same thing for my 4A, I have to do a reversed one. So this is quite interesting. I don't know why. But somehow I managed to get my diagram done. So first of all, I tried by hand. So I did careful units measuring here, draw in scale, and got 100, 200, between 200 300. This is my 224 value, and this is my negative 271 point here. So I just construct the point using a ruler. I just make sure, make sure this angle here, 3A, is going to be 3A is going to be 33 degrees over here, and my 1A is 39 degrees. So my 1A is here, so this big angle here, 31 degrees. So hang on, sorry, this is 39 degrees. 39 degrees, and this is 33 degrees. So the same thing for 4A and a 2A. So this is 2A and this is 4A. Yes, sorry, the other way around. This is 2A and this is 4A. So this is the same thing. You just draw your line here. Make sure this alpha angle is what you calculated. So that's it. So this is the Magnel diagram. So jumping onto here, this is a presentation wise. I just scale it up over here. So once you've got your Magnel diagram, and you can easily spot that within all the lines, there is a common area, a trapezoid area, little skinny like corridor here. So within this area, you can pick any number that is going to satisfy all four equations. So for me, I'll just say, okay, I'm going to pick a point over here. This is within this trapezoid area. So this is going to my eccentricity. I'm going to call it whatever, 560 something. And then my coming up to the left, so my prestressing force is going to be 1 over pi is 0.00027. And your pi value is going to be, you have to divide that. So get your pi value. So your pi is actually, so it's going to be 1 over 0.00027. And if we do that, 0.00027, and it gives about 3,703 kilonewtons. So that is your prestressing force that you need to induce into your prestressing element. So yeah, that's it. Thanks for watching.